Hi, my name is Yifan Wang from the School of Agriculture, Biomedicine, and Environment at La Trobe University. I am a PhD student who is finishing up the thesis in 1 or 2 months and will graduate soon. In this video, I would like to introduce a new coating material. The surface coating solution we will develop in the frame of this grant is based on a material called beta-3 peptide analog. This peptide analog resembles both polymers and peptides, offering extremely versatile building blocks for nanostructured materials. These peptide analogs are derived from standard beta-3 peptides with either N-terminal acetylation or C-terminal imidation. These modifications do not affect the overall helical conformation. The analogs maintain a stable 14 helix with a 15-degree sidechain offset. The additional carbon in the beta-3 backbone allows great chemical functionalization. Space filling modes shows dense packing that shares backbone amide groups, providing good resistance to degradation in both acidic and alkaline environments comparing to natural alpha peptides. The beta-3 peptide analogs form 14 helices stabilized by intramolecular hydrogen bonds. With terminal modification, each helix contains 3 NH groups at one end and 3 carbonyl oxygens at the other end of the helix, enabling head-to-tail assembly via 3 pairs of hydrogen bonds. And we call it 3-point hydrobonding motif. This leads to the formation of supramolecular fibers. The fiber morphology is sensitive to experiment conditions. Structure varies due to the change in solvent and temperature displayed in Figure 4, and in Figure 5 you can see the change in sequence order also shift the fiber morphology significantly. A specific sequence, unacylated AVS HESIS AVA, also we call it HESIS peptides, was designed to assemble into metal supramolecular frameworks, which is MSF, and in this sequence, A, V, and S are beta-3 residues, while the 2 central histidine are in the alpha configuration. AFM and TM confirm fiber formation through a 3-point hydrogen bonding motif, and XPS analysis support a 2-step assembly process, initial 1D fiber formation, followed by 2D framework construction through metal coordination with copper. The MSF formed from HESIS peptide analogs has a potential application in green energy as the functional coating for solar panel surfaces. Recent rheological measurements demonstrate self-healing behavior of the beta-3 peptide analogs network, enabling recovery from surface damage. By turning the peptide sequence, the coating can achieve amphiphobicity, repairing both polar and non-polar substance to enhance resistance to moisture, dust, and organic contaminants. Importantly, the MSF assembles under mild conditions and requires no vacuum or plasma treatment, enabling easy, scalable, and cost-effective surface modification for photovoltaic applications. This research involves ongoing collaboration with internationally recognized facilities and the use of advanced techniques such as vibration sun-frequency generation with ultra-fast laser system and scanning near-field optical microscopy with synchrotron beamline in order to characterize the peptide analogs. We aim to translate research into practical applications of green energy. Funding from the National Foundation for Australia-China Relations will support further collaboration with researchers and institutions in China to advance application-oriented development of this self-assembly system.